This video discusses applications of maximizing and minimizing quadratic functions. The maximum minimum value of a quadratic function always occurs at the vertex. If your parabola is pointing up, the minimum value is located right here, which is at the vertex. Similarly, if you have a parabola pointing down, the maximum value occurs right there, also at the vertex of the parabola. When solving these applications, you need to determine whether you're looking for the x or the y coordinate of the vertex. You'll make that determination based off of the context of the application. We want to find the height, s, in feet of a rocket after t seconds. This function is given by the formula s of t equals 192t minus 16t squared. Let's find the height of the rocket. In this example, it's nice because they gave us the formula. The first thing I would do is I would rewrite that quadratic function in descending order. I don't want to accidentally grab the wrong number when I'm finding the vertex. Now let's determine whether we need the x or the y coordinate of the vertex for our solution. They're asking us to find the maximum height. So which variable was the height? Just look at it. Says that the height is s. Looking at our quadratic function, where's the s located? Over here on the left, where y is typically located. Therefore, we're looking for the y coordinate of the vertex. When a quadratic function is in general form like this, there's no way to go directly to the y coordinate of the vertex. We're going to have to use our vertex formula, find the x coordinate first, then plug it in and find the corresponding y coordinate. So we're using our formula that says x equals negative b divided by 2a. Our x value is actually t, so you may see it written t equals a negative b over 2a. Either way, we're going to have a negative 192 over 2 times negative 16, which is negative 192 divided by negative 32, which is 6. That's the x coordinate of our vertex. What we need is the y coordinate. To get the y value, we're simply going to plug 6 into our function. So y is going to be s of 6. And when you plug that into your calculator, we get 576. Since it's an application problem, remember to put your unit on it. S represented a height that was said to be in feet, so this is 576 feet. In our next example, the quadratic function was not given to us. We are going to have to derive that function. Two identical rectangular chicken coops are to be built adjacent to one another using 120 feet of fencing. The first thing we want to do is draw a diagram. Let's see what these chicken coops would look like. So we have two identical rectangular chicken coops. That's pretty identical. The first thing I ask is, what do we know about these three sides, since we have two identical adjacent rectangles here. We don't know the measure of those sides, but we know that those three sides have to be identical. I also want to note that if you're building two fenced-in areas right next to each other, you would not put a double wall of fencing in the middle. Like, we would not have a second vertical line here. We would try to save fencing and use that middle wall for both pens. If we read on to the problems, what dimensions should be used to maximize the area of an individual coop, and then what is that maximum area of the individual coop. So you'll see over and over they're talking about area of the individual coop. We're going to need to write an area function here. We know that area is equal to length times width. And they mentioned the area of an individual coop over and over again. So we're going to want to get the length and the width of one of these coops to create our area function. Well, we already know what the width of our individual coop is. It's x. But now we need to figure out what the length is. We have not used the piece of information yet that we have a total of 120 feet of fencing. If we have 120 feet of fencing total, so far we've used up 1, 2, 3 X's of fencing. So how much fencing would we have left? Well, we're going to have 120 minus 3x feet of fencing left for the 4 lengths. Well, I need to know how long just one of these lengths are. To figure that out, we take the 120 minus 3x and divide it by 4. And this can be simplified to be 30 minus 3/4 x. Now I have the width and the length of an individual chicken coop, and I can write my area function. So our area is going to be equal to our length times our width. It's going to be 30 minus 3/4 x times x. Distributing, we get a of x equals 30x minus 3/4 x squared. As in the previous example, I'd be inclined to rewrite this in descending order. Now that we have our function, let's answer our questions. Part A asks us what dimensions should be used to maximize the area of an individual coop. So in part A, they want us to find dimensions. Which variable is that going to be, the x or the y coordinate of our vertex? If you look at our diagram that lists the length and the width, which would be the dimensions, what variable are we using? X. So in part A, we're looking for the x coordinate of the vertex. So let's find that. Using our vertex formula, x equals negative b divided by 2a. It's going to be x equals negative 30 divided by 2 times negative 3/4. Negative 30 divided by negative 3/2. We get x to be equal to positive 20. If we reread the question, they ask for the dimensions of the individual coop, which would be both the length and the width. So far, we've just found the width. We need to make sure to answer the question here. So our width is going to be 20 feet. Our length is 30 minus 3/4 x. So plugging 20 in for x, our length will be 30 minus 3/4 times 20. We end up with a length equal to 15 feet. So those are our dimensions, 20 by 15. Now I want to take a look at part B. Part B says, what is the maximum area of the individual coop? So this time we're looking for the area. Taking a look at our function, area is over here, where y usually is. So in this case, we're looking for the y coordinate of the vertex. So we can find our answer here by taking our x value, which was 20, and plugging it into our function. But there's probably an easier way to do that. We know that area of a rectangle is length times width, and we know what our length and width are. Our area is going to be 15 times 20, which is 300. And remember to include your unit, feet squared. We would have got the exact same thing had we plugged 20 into our area function and found a of 20.